Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall solve some problems on limits of functions of complex variable. Earlier lecture, we have defined what is the limit of complex valued function, and we have solved one problem also. We shall solve some more problems on finding limits of complex functions using the definition of limit. See, earlier in our earlier lecture we have defined limit of complex functions. That is, if we say limit z tends to z naught of f of z is equal to w naught, this is defined if for every epsilon. So, this is if for every positive epsilon or epsilon in short greater than 0, there exist positive number delta. Epsilon and delta are positive numbers, small positive quantities or small positive numbers are denoted by Greek letters epsilon and delta. For every epsilon greater than 0, there exists delta greater than 0 such that the absolute difference of fz and w naught, this is less than epsilon whenever 0 is less than z minus z naught is less than delta. That means when z approaches towards z naught, then this f of z approaches towards w naught. That means becomes closer and closer to w naught. The distance or difference, the absolute difference of this is less than epsilon, a small quantity, whenever z naught lies in this z lies in the deleted neighborhood of z naught, delta neighborhood of z naught, or that is distance between z and z naught is less than delta. So, this is the definition of limit that we have studied earlier. Now, we shall use the same definition to show these two limits. Now, we shall consider the solution of first to show this limit. To show limit z tends to z naught of z bar, conjugate of z, is equal to z naught bar. We have to show according to this, but you see what is z and what is z bar. We have z is equal to x plus I into y, and what is the z bar? Z bar is conjugate of this, and we know it is x minus iy. And what about z naught? Z naught we have is that z naught is equal to x naught plus iy naught, and what will be z naught bar is x naught minus iy naught. And now we shall show this limit. To show limit z tends to z naught of z bar is equal to z naught bar, we have to show that according to the definition. We have to show that for every positive number epsilon, however small it may be, there exist, or we have to find delta. For we have to find delta, there exists delta greater than 0, or there exists a positive number delta. Such that, see, we are using the same definition, such that the absolute difference or absolute value of this difference z bar minus z naught bar is less than epsilon whenever 0 is less than z minus z naught is less than delta. That means the difference, absolute difference of z and z naught is less than delta, or z lies in the delta neighborhood of z naught. That is according to the definition. Now, we will suppose this as 1, and then we have to find delta. Given epsilon greater than 0, we have to show that there exists delta greater than 0. So, we shall suppose this as 1. Now, we will consider this mod z bar minus z naught bar, and this can be written as this is equal to z minus z naught bar, because we know this property of absolute function, since see z1 bar minus z2 bar is equal to z1 minus z2 bar, or reverse way. This property is used, and again this is equal to z bar minus z naught bar is equal to z minus z naught, and because the absolute value of the conjugate of z is same as absolute value of z, since these are results from absolute value function, mod of z bar is same as mod z, and thus mod z bar minus absolute value of z bar minus z naught is same as the absolute value of z minus z naught, and here this can be replaced, and therefore from 1 mod of z bar minus z naught bar less than epsilon means z minus z naught is less than epsilon. And therefore, this is same as z minus z naught is less than epsilon, and we want to select delta. Now, we want to make this as smaller than epsilon, and therefore, we select this delta is equal to epsilon, then the statement 1 will hold. So, therefore, we select or we choose delta is equal to epsilon. Delta, we want to find there exists a positive number delta, that means we have to find delta, and this delta we can select as epsilon, and if you select delta as epsilon, this inequality is same as z mod z minus z naught is less than epsilon, and if we select epsilon is equal to delta, this is satisfied. So, therefore, we select delta is equal to epsilon, then this statement 1 holds, then one holds, or that is true, this statement is true, because we have this means z minus mod of z minus z naught is less than epsilon, and we select delta is equal to same as epsilon, then this statement becomes true. So, that is this z bar minus z naught bar becomes less than epsilon whenever 0 is less than mod z minus z naught is less than delta is true, and this proves limit of z bar is equal to z naught bar. So, we can write this proves limit z bar as z tends to z naught is equal to z naught bar, and thus we have proved the result, and here we have selected simply delta is equal to epsilon, because the inequality is same, and if this delta is taken as epsilon, the statement 1 becomes true. Here we want to find the value of delta. Now, we shall consider second problem, solution of second. Here what we need to prove is limit of this, suppose this is f of z and this is z naught, we have to prove limit f of z as z test z naught is equal to w naught, we suppose this as w naught. So, first thing is, let as earlier z is equal to x plus I into y, f of z is equal to x plus I into 2x plus y, this is f of z, and z naught is equal to 1 minus I, and w naught is equal to 1 plus I. As comparing this with limit z tends to z naught, f of z is equal to w naught. We have selected these values, and now to prove this, actually to prove the given limit, to prove the result or this limit, to prove limit z tends to 1 plus 1 minus I, f of z, this is f of z, is equal to 1 plus I for every epsilon, for every positive epsilon. We have to find delta, positive delta. A positive number delta such that this f of z, difference of f of z and its limit 1 plus I, absolute difference of this is less than epsilon whenever zero is less than z minus z naught. What is z naught here? Is 1 minus I. 1 minus I is less than delta. So, this we have to show, and we shall assume this as our statement 1. This condition we have written according to the definition of a limit, that the difference, absolute difference of this fz and its value is less than epsilon whenever the difference of this z and z naught is less than delta. We have to find this value of delta, and then the result statement 1, if statement 1 holds, then the required limit is proved. So, first we shall simplify this. Let this 0 is less than mod z minus 1 minus I. 1 minus I is less than delta, and we shall consider the right sides inequality, that is mod z minus 1 minus I. This we shall simplify. Now, or first we shall consider this value, absolute value of z minus 1 minus I, and we know what is z. Z is x plus I into y, and therefore this is equal to x plus I into y minus 1 minus I, or this is equal to absolute value of x minus 1, real part we shall write separate, this is real part x minus 1, and then imaginary part, that is I is common, plus I into bracket y, and this minus of minus becomes plus I is taken common, so in bracket it is y plus 1. So, this is the value of z minus 1 minus I, and now we know that the absolute value of function, real value of z is less than absolute value of the function, also imaginary value of z is less than absolute value of the z. So, this result we have, what is z, if z is equal to x plus I y, then real z is x and imaginary z is y, and we have here as x is less than or equal to absolute value of x, absolute value of x is less than or equal to absolute value of x plus I y, or that means real z, absolute value of x means real z, mod of real z is less than or equal to mod of z, and similarly mod of y is less than or equal to absolute value of y is less than or equal to absolute value of x plus I y, and this is obvious because what is the absolute value of x is root of x square, and what is the absolute value of x plus I y is under root of x square plus y square, I into y whole square, not I but only y square by definition, and this the inequality between this is less than or equal to. If y 0, then the two will be equal, otherwise this value is less than this right side value. Similarly, under root of y square, what is mod y means under root of y square, and that is less than or equal to under root of x square plus y square, and that means these results follows as imaginary z, absolute value of imaginary z is less than or equal to absolute value of z. And thus now what is the real part of this complex variable is x minus 1, and what is the imaginary part of this number is y plus 1. So therefore mod of x minus y according to this real z, or we may write this as since C, then this value mod z minus 1 minus I is less than delta gives or implies absolute difference, absolute value of x minus 1 is less than or equal to this whole real number is mod z minus 1, mod z minus 1 minus I, this means, and this is less than delta. So because real z, absolute value of real z is less than or equal to absolute value of z, and what is the imaginary z? Imaginary z is y plus 1, its absolute value is less than or equal to the same, that is mod of z minus 1 minus I, and that is less than delta, since you may have this in bracket, since this one, and it is obvious because according to this absolute value difference it will be root of x minus 1 whole square, and this is root of x minus 1 whole square plus y plus 1 whole square, and the inequality between these two is less than or equal to like this, and thus we have, suppose this as a second statement, we have supposed that as 1, this as third statement, and now we shall consider our required inequality. See, we want this to be less than epsilon, and in that condition we want to find out delta. So I shall write here now we want mod of f of z minus 1 plus by 1, statement 1 plus I is less than epsilon, and now we will consider this again. Now mod of f z minus 1 plus I, and this is equal to f of z is this one, that is x plus I into bracket 2x plus y, this is f of z minus 1 plus I, and this means we will simplify this and separate its real part and imaginary part. So what will be this? This will be x and minus 1 is real part plus I into bracket 2x plus y, and here I is minus I, and therefore here is minus 1. And we will now use the property of absolute value function, which is known as triangle inequality, and that can be written as, see here, this will be less than or equal to mod of x minus 1 plus mod I into mod of 2x plus y minus 1. So which property we have used is mod of z1 plus z2 is less than or equal to mod z1 plus mod z2 by triangle inequality, since mod z1 plus z2 is less than or equal to mod z1 plus mod z2. So this property we have used, and again you see what is mod I? Mod I is 1. So it is I means 0 plus 1 into I, and its absolute value of is equal to 1, under root of 0 square plus I square, which is 1, and therefore mod I is 1, and this is 1, and therefore this quantity is now equal to, So I shall write this equal to, this relation is equal to mod of x minus 1 plus, but there is a less than or equal to sign between extreme left and extreme right, and now this expression is equal to x minus 1 plus mod of 2x plus y minus 1, and again this can be written as mod of x minus 1 plus, I shall write in this bracket, we want to use this result 2 and 3, and therefore I shall write this as 2 into x minus 1 we want, and plus, and we want y plus 1, so therefore in bracket it will be, it is minus 2 and plus 1 is minus 1. So the value is not changed, 2x minus 2 plus y plus 1, and that is the same as 2x plus y minus 1. You may verify this. So thus we have written this as this function or this expression as like this. And now what is the extreme left side? F of z minus 1 plus I, and that we shall keep as it is. And what is relation between this one and that one is less than or equal to, and thus therefore this I shall write here, this I shall continue here, less than or equal to mod of x minus 1 plus, and again you see this will be less than or equal to, again triangle inequality, mod of, we will separate this, mod of 2 into x minus 1, and that mod 2 is 2 again. So therefore this is 2 into mod of x minus 1 and plus mod of y plus 1 by triangle inequality. We have separated mod using this, and the inequality is again here, that is less than or equal to, I have written that step here, and by triangle inequality you may write, since or the same inequality, z1 plus z2 is less than or equal to mod z1 plus mod z. And now what is this? This will be now equal to x not equal to, but you see, what about mod of x minus 1? Mod of x minus 1 is less than delta. This extreme left is less than or less than delta, strictly less than delta, and mod of y plus 1 is also strictly less than delta, and therefore this is less than delta plus 2 times delta. Each quantity here is less than delta from second and third. So this is delta, this is 2 times delta, and this is again delta. So which is equal to 4 delta, and thus what is the relation we have? This f of z, mod of f of z minus 1 plus I, thus mod of f of z minus 1 plus I is less than, strictly less than 4 delta. If we have considered this as mod of z minus 1 minus zeta, mod of this is less than delta, then this expression is less than 4 delta, and this suggests us for the choice of value of delta, and that choice can be now taken as this value is epsilon. If you want, we want this relation, and therefore we choose this as epsilon, and that means delta should be 4 delta is equal to epsilon. So therefore if we choose we choose 4 delta is equal to epsilon, that is delta is equal to epsilon by 4. Whatever epsilon is given, choose delta as epsilon divided by 4, 1/4 of that value as delta, then this inequality holds and this statement also holds. Then this f of z, mod of f of z minus 1 plus I will be less than epsilon, then statement 1 holds. One holds for this delta, and this proves the required limit. this proves the result. This is the result, and thus we have shown the limit of this function as z tends to 1 minus I is 1 plus I. Now we have earlier proved a theorem that limit of a function, if it exists, is unique. Now when we will solve a problem to show that the limit does not exist. It is not always the case that limit exists. Sometimes the limit does not exist. So here we will write a note as if limit z tends to z naught of f of z is equal to w naught, if it exists, c is equal to w naught will exist, and so then this exists, then z tends to z naught in any arbitrary manner. And not in a particular direction or particular way. So what is meaning of this? Here z tends to z naught means this is z naught, deleted neighborhood z naught, and z is within the neighborhood of this z naught. Z is here, and this radius of this disk is delta. So z may approach z naught in any way. So if z is here, then it will approach here. If z is here, then it will approach towards z naught in any direction. Then the limit holds, or that is the condition for the limit, and not in a particular direction. So we will use this condition or this result to show the limit does not exist of following problem. In the following problem, we shall consider it as a second problem. Show that limit z tends to 0, z divided by z bar does not exist. This limit does not exist. Solution for this. Now if this z tends to tends to 0, limit of z tends to 0 as z of divided by z bar exists, then z must approach 0 in any manner. If limit z tends to 0, z divided by z bar exists, then z will approach, then z tends to 0 in any manner and not in a particular direction. Now what we will consider is z will approach towards real axis first. Now suppose z is equal to x comma 0 on real axis. Y is 0, is a non-zero number on the real axis. That is x axis, and z approaches 0, that is x comma 0 approaches 0 comma 0. Then we shall find out what is the limit of this z upon z bar. In this case, limit z tends to 0 of z divided by z bar is equal to limit. What is z? Z is x comma 0 and tends to 0, 0 comma 0. Z, what is z? Is x plus iy. And what is z bar? Z bar is x minus I into y. and therefore what will be this? So this will be, now you see here y is fixed to be 0, and therefore we shall put the value of y directly as 0, and what will be this? This limit will simply becomes limit x tends to 0 of x plus I into 0 divided by x minus I into 0, since y is fixed to be 0 on real axis, y is 0. And what will be this now? This will be limit of x divided by x. And what is x divided by x? X divided by x is 1, and therefore this is limit of 1, and limit of 1, a constant quantity, limit is 1. So therefore this will be 1, the limit is 1. And now we will consider this as a result first. What we have obtained is limit z divided by z bar is equal to 1. Now we shall suppose z is 0 comma y, that is a point on imaginary axis. Next, suppose z is equal to 0 comma y, a non-zero number on the imaginary axis. And z tends to 0, that is 0 comma y tends to 0 comma 0. Now this case I shall write here. In this case, what is the limit of limit as z tends to 0 of z divided by z bar? This is limit 0 comma y tends to 0 0 of z is x plus I into y and z bar is x minus I into y. That is the usual value of z and z bar. And now here x is fixed, so we have to put x as 0, and thus the limit reduces for only y. Y tends to 0, 0 plus I into y divided by 0 minus I into y, and again this I into y cancels from both sides, and what remains is minus 1, that is a fixed number. So this is limit y tends to 0 of minus 1, and which is equal to minus 1. So this limit is minus 1, and we may suppose this as second. See, from the first result, we when we say z tends to 0 from real axis, then the limit is 1, and when z approaches 0 from imaginary axis, the limit becomes minus 1. So, but we have proved the result as, but limit z tends to 0 or z tends to z naught of f of z, or limit of a function f of z at z naught, at a point z naught, if it exists, is unique. But limit of a function f of z at a point z naught, if it exists, must be unique. This theorem we have proved in our earlier lecture. You may please watch that result, that lecture, and it must be unique. And here the two limits are different. From 1 and 2, we conclude that the limit does not exist. Therefore, by 1 and 2, we get limit f of z, this z bar does not exist. We get this result. Now here what we have seen is there are two approaches for x, z tends to 0. See, this is origin x and y. First we have considered x on z on real axis, that is this x comma 0, and it is approaching towards origin. This is z, and next we have considered this as 0 comma y, and then it is approaching towards y. Two directions we have considered along real axis and along imaginary axis. We get from this direction we get the limit as 1, and from along the imaginary axis we get the limit as minus 1. So the limit cannot be different, and therefore here we say that limit does not exist. As in real valued functions, if you get the left hand limit and right hand limit different, then we say limit does not exist. The same thing here, the limit does not exist. Now I will give you one problem to for your practice. Use definition of limit to show limit z tends to z naught of real z is equal to real z naught. Use the definition and show this result. So I hope you can you will understand this solutions of these problems. Thank you for watching the lecture.